Fourier theorems, maybe the most mathematically tedious section of the class, right? I apologize to those of you who don't want to see things that way, but we can draw lots of pictures too. So, and then next week we start the applications section, which is really seeing demos of things in action. So it'll get more interesting then. But it's good to understand this stuff. The thing about these Fourier theorems is that they give you a thinking vocabulary for spectrum analysis, and that's really worth having. So I just thought I'd pick up on one little aspect of what we talked about last time. Remember the NDFT. We sort of ran out of time right when I was going to make some of the Fourier theorems be pretty, using the normalized DFT. So x tilde of omega sub k is defined as the projection onto s tilde sub k of x. And that means that we're going to take the inner product of x with sk tilde. And sk tilde is our normalized DFT sinusoid. Normally we do not normalize. So let's look at the definition of that expanded. So we take the inner product of x sub n sk tilde bar of n. And that is equal to the sum over n of x of n e to the minus j omega sub k t sub n over the square root of n. And so the square root of n is what's normalizing this to give us that the norm of sk tilde is equal to 1. So that's the sense in which this is normalized. And we can pull this 1 over square root of n out in front and see that it's just a regular DFT divided by square root of n. So I'm keeping all the same notation. I'm not redefining any notation. I've got a new transform, the NDFT. So this gives us a very easy way to update the Fourier theorems. So to summarize, I'll say x tilde is equal to 1 over square root of n x. That's a nice simple notational summary of that. And so, for example, recall the power theorem. The power theorem was that the inner product of two signals, x and y, is equal to 1 over n times the inner product of their spectra. Well, we can write that as the inner product of the first spectrum divided by square root of n times the inner product with the other signal spectrum divided by square root of n, which is by definition the inner product of x tilde with y tilde. So this is an example of how the NDFT will clean up some of the Fourier theorems, especially anything to do with normalization of energy and such. And this actually should be what you expect, because remember that the inner product is defined as the cosine. That's how we define the cosine of the angle between two vectors in an n-dimensional space. I think the way we said it was that the absolute value of the inner product of was defined as the cosine of the vector angle. So you would expect that if you have some signal space and you have some vector in it, x, and you have some other vector in it, y, and then you have an angle between them, you would expect that it shouldn't matter what your basis functions are, right? In other words, whether the coordinate axes are the shifted delta functions or sinusoids, whatever basis we choose, the two basis sets should be unable to change the angles between vectors, and that's the case. So when things are properly normalized, you get that, and so that's why the normalized DFT is really the right thing. You know, we really should be using that mathematically, but from a practical point of view, it requires dividing by the square root of n, and nobody wants to implement that because why? You know, so you just keep track of scaling to the end base. So you don't do any scaling until the very end. If you're in floating point, if you're in fixed point, you're scaling all over the place. In fixed point, when you do an FFT is arranged as a sequence of butterfly stages. You'll do scaling in between each butterfly stage. So you'll, for a length 1024 FFT, you'll have like 10 scalings in between all your butterfly sections. So you'll scale all the time in fixed point. So avoid fixed point. Just do everything in floating point. You know, I say that, but you'll find yourself sometimes having to do fixed point when you're on a small VLSI segment of a chip or something like that. So that's an example of how things can get cleaned up. Any questions about the NDFT? We could go on about that, but I think it's pretty straightforward. All you have to do is you know, plug this in everywhere. So everywhere you see an x, you can put in, you know, square root of x tilde, square root of n times x tilde, and just play with it. So the ones that have 1 over n coming out will get cleaned up. And most of them won't make any difference, right? Shift theorem doesn't change. Doesn't matter how you normalize things. It's, you know, relative to itself, basically.